Bonjour. Good morning. Thanks for coming. I wanted to start by thanking the organizers, but I really would like us all to thank the organizers, so I think they really deserve a nice round of applause. It's really been a wonderful conference so far, and one reason I like to do that is that I've just started with gratuitous applause for this talk. We're going to do this jointly, so let's see if this works. This is older work. This is a survey of some older work. There's a little bit of newer work sort of embedded in the middle, but we wanted to do this for a couple of reasons. I'd say the main one is that this is sort of a tribute to Henry Crapo, who lives, a couple of 100 kilometers north of here. The last time we were in France was 10 years ago. He had a very small conference at his residence where he has a mathematical center. And it was a tribute, actually, to my PhD advisor, Tom Brylawski. Henry's house is there. Yeah, it was a very nice time. So in the 1960s, Henry produced this catalog of matroid extensions, and if you can't read that, it's actually English up there. So I don't know if you can read this, Henry Crapo, well, there it is, color-coded. The Henry Crapo group presents the incredible catalog of point geometries, of 8-point geometries. See single element extensions grow before your eyes. This is actually related to the first talk of this conference when James Oxley was talking about extending a matroid. Given how trippy this is, it's pretty easy to guess this was a 1960s catalog. So what I'm going to do is I'm going to talk about the beta invariant for graphs, and I'm going to talk a little bit about matroids. Then I'm going to talk a little bit, very briefly, about anti-matroids, but for the most part, Liz is going to take over from there. So when you get tired of hearing one voice, you get to hear somebody else. So what we're going to do is we're just going to start with this invariant, and given a graph, define the rank to be the size of the largest acyclic subset. So I'm thinking of the ground set as the set of edges of the graph, and this rank function is the matroid rank function that you usually get when you think about the cycle matroid of a graph. So here's an example of K4 minus an edge. We'll compute the rank of every subset of edges. So all 32 subsets, the ranks are listed here. Of the sets of size 3, there are 8 spanning trees and 2 triangles. The spanning trees have rank 3 and the triangles have rank 2. And then you can assemble that information into this formula computing this beta invariant that Crapo defined. And here's what you do. So the empty sets contribute 0, singletons contribute 1, but there's a negative 1 to the size of the set that's part of the formula. Pair contributes 2, these triples contribute negative 2, and so on. And you just use this formula and you sum it up, and in this case you get the number 1. So the number 1 means something, presumably. Crapo defined this originally, actually he defined it for matroids in 1967. This is his paper. This is in JCT. This is before there was a JCT A or B. It was just JCT, Journal of Combinatorial Theory. And his abstract talks about his motivation, which sort of curiously begins by saying what the Mobius invariant doesn't do. He had very much, at this point, I think, a lattice theoretic view of matroids. So you think of the lattice of flats, which is this geometric lattice, and The Mobius invariant was popular, but was not, as he says, is less useful in studying exchange geometries, which was his word for matroids at the time. So he introduced this number beta, which was more controllable and also has a nice duality property. The beta invariant for a matroid is equal to the beta invariant for the dual of the matroid, provided the matroid has more than one element. So it's actually interesting to read these old papers. He has a lot of the main results in terms of what this invariant was in this original paper, including lots of different formulations that are equivalent, and one of probably the main theorem, at least at the time. So it's related to the Tutte polynomial, and in fact he has that in there. If you write down the Tutte polynomial of the graph or the matroid, then the coefficient of the term, the x term, is one way you can define this polynomial. Coefficient of the x term and the y term agree if the matroid has more than one element, which is a nice fact that's not hard to prove. And the I'm not going to define the Tutte polynomial, but Liz and I had done a lot of work on that back in the 90s. This sort of grew out of the work on the Tutte polynomial. Given that it's got a Tutte polynomial expansion, it's not surprising that there's a deletion-contraction relationship that holds for this thing. And that turns out to be very useful for doing computations, as you can imagine. So if you delete this middle edge C, you get this thing, a cycle. And you can show that for a cycle that this invariant is always 1. If you contract, you get this thing, which is not too connected. So as a matroid, it's not connected, and it's easy to show that. So in terms of the rank function, this thing is a direct sum, and it's easy to show that the beta invariant is 0 in that case. So I get 0 from this thing and 1 from this thing, so the total invariant is 1. One consequence of deletion contraction is you can use induction, just to show that the beta invariant is always a non-negative integer. So that's a nice fact. And it also gives you some hope that you can try to interpret this thing combinatorially, or at least get some information about it. Now that I'm a good 7 minutes in, I should ask, can everybody hear me? One of the extensions that we looked at, and this material actually is fairly new in the sense that we were working on it in the last 24 hours. You can define the exact same invariant for a rooted graph. So I've got a graph now and I've got a distinguished vertex, and here's what I want to do. I want to change the rank function. It's still going to be defined on edges, but I need a new rank function. So the rank of a subset of edges is going to be the size of the largest rooted subtree that lives inside that set. We're going to get something different. The contributions are going to be, well, they're listed down here, but for example, if I take this set CD, that's 2 edges, but its rank is 0. Because there is no subtree that intersects that at all. If I take ACE, that triangle, the rank is 2, which is exactly what it was before when I didn't have the distinguished vertex. But this obviously pays a lot of attention to the location of that vertex. And then you can go through and just mimic the same formula. And in this case, you get an answer of 3. In fact, for this graph, if you place the root at the top there, you get 3. If you place the root at, well, I could have rotated this thing. If you place the root at the other vertex, you get beta equals 4. Right now, I would say an open question is this worth looking at? Is this worth even thinking about at any length? And I don't have a good answer for that. One of the problems is that it's not clear what this beta is measuring. I'll give you a few more examples in a minute. And when you compare it to what Liz is going to talk about, there's a very clear combinatorial interpretation for beta later on. So right now, this looks like just random information. There is a deletion contraction that works in this case too, though, for the rooted case. You do need to insist that the edge that you're deleting and contracting is adjacent to your rooted vertex, your distinguished vertex. So you still get that these numbers are greater than or equal to 0. By the way, that's something else that's going to go away later in this talk. You'll get negative numbers for beta. Here's a list of comparing the unrooted case, which is the standard one that Crapo did. In fact, in that original 1967 paper, Crapo computes it for trees, cycles, wheels. He could have done fans if he'd wanted, and complete graphs. How does that change when we put a root? Well, for a tree, the only time it's 1 is if you have a path and the root is at the end of the path. Everything else is 0. Cycles, this is now going to measure the number of edges in the cycle. Fans, the same thing. And these are all fairly straightforward to prove using deletion and contraction. Wheels and complete graphs. And you'll notice that in each case, except for the first case, that the putting a distinguished vertex seems to increase the size of this thing by about a factor of n, or n minus 1. And when I say rooted for the wheels, I'm rooting it at the center. If you root it off the center, it appears that the beta invariant is even larger than that number, n times n minus 1. Okay, so now I'm going to move to matroids. It's nice to have a talk where I'm introducing matroids, where I don't have to introduce matroids. So if you have a matroid, you have the exact same definition. All of these results were actually in Crapo's original paper. So beta is the same for the dual as it is for the original matroid. Direct sums give you 0. It's non-negative, and it has this deletion contraction. The main theorem from that paper was if you have more than one point and your matroid is disconnected, that's characterized by this beta equals 0. Beta can also be 0 if you have one point and it's a loop. So that's this one special case. That's why you see all these theorems. You need more than one point. So beta here is 0. This is a disconnected matroid. Brylawski was able to generalize that by characterizing when beta was 1. It turns out beta is 1 precisely when you have a series parallel network that's giving you the matroid. And here are 3 matroids in increasing order. This is K4 minus an edge. This is K4, which is not series parallel. And it has nothing to do with this talk, but I always would feel bad if I had a talk and I didn't have the Fano plane somewhere in there. So there it is. And you can push this a little bit farther, and in 1982, James characterized when beta was less than or equal to 4. So you can get some sort of characterization of when you get small values for beta. So there's a hope that you could possibly do something like that for the rooted case, maybe. Okay, so I'm going to talk a very little bit about anti-matroids, and then Liz is going to tell you about special cases of anti-matroids where this thing really measures something that you care about. In fact, if you don't care about anti-matroids and you don't care about the beta invariant, then the second half of the talk is going to be for you, because you're just going to see combinatorial theorems that you can remove all of this sort of structure from. You'll get nice results, but she'll tell you about that. So the way I want to define this is you start with a closure operator on a set. And closure operators have these nice properties. If you start with a set, so you think of this as a map from the subsets to the subsets. A set is contained in its closure. It has this monotonicity property and this idempotence. So that's what closure operators are. And you can see these in topology, obviously. In order to make it a matroid, you need this one additional axiom, this McLean-Steinitz exchange axiom. So if I've got 2 elements, so think of this as a set A, so there's a flat in a matroid. X and Y are not in that closed set. if y is in the closure of A union X, so here's A union X, if I take the matroid closure, then I have to pick up y, and vice versa, then X is in the closure of A union Y. So that's the standard matroid closure axiom. For anti-matroids, and the reason they're called anti-matroids is, you'll see, it looks almost the same at the beginning. Well, it is the same at the beginning. You've got two elements not in the closure of A. Y is in the closure of A union X, and then you have to negate this containment. So then X is not an element of A union Y. Matroids you should think of in terms, at least the closure operator is affine closure. Anti-matroids, it's more like convex closure. This is the cover of the third book in a series of books that came out in the 90s that Cambridge published, Matroid Applications. On the cover is an anti-matroid, so, which annoyed my advisor quite a bit. Why would you put an anti-matroid on the cover of a book about matroids? But notice that X and Y are not in, so A is this croissant-shaped thing, and Y is in the closure of A union X. So the closure here is convex closure, so just think of this as convex Hull operation. But notice that X is not in the closure of A union Y. These were a series of Matroid books, Matroid texts that were edited by Neil White. There are people in the room who have contributed chapters to this book, these books. Some of them were extremely valuable for a lot of people. This is the only picture I found of Neil White on the web. Neil was very important to me. I think I had a class from him every term as an undergraduate except my first term in college. He taught me algebra, problem solving, combinatorics, and then algebra again. Yeah. And I think this was taken in Park City, Utah. And I think this is my last slide. Oh, note, wave to Michael Fong. Hi, Michael. Well, I think you were hand waving about anti-matroids before. So the term was coined by Robert Jameson in '80, but they've been in the literature for many years before that. They seem to be discovered and rediscovered a lot. My favorite are these LSD, these lower semi-distributive lattices, was what they were called in the '60s. Again. And then this sort of abstract convexity stuff was really developed by Jameson and Edelman in the '80s, and I think that's probably what you were referring to. Yeah. And now it's Liz's turn.
Thank you. Here. Thank you. Hi. So, yeah, trees are anti-matroids, so they're a nice example of anti-matroids. So, what we're going to do for most of what we're going to do is think about convexity. So we're going to actually use the convexity, an expansion for the beta invariant. So we start with an anti-matroid with ground set E, and that has a convex closure operator. So from that, you can define the convex sets. So a set is convex if it's its own closure. You define feasible sets, different from the feasible sets we saw yesterday morning. So a feasible set is, its complement is convex. And you've got a rank function. You can define a rank function, the maximum feasible set. And that's really what the matroid definition was using. So the beta invariant, notice this is exactly the same as we had before. So we're just going to take the same thing, but we're going to actually reconfigure it. So a set is called free convex, or we'll often just say free, if every subset of it is convex. So it's not enough to be convex. You have to have every subset also being convex. And then for an anti-matroid, here is a convex set expansion for the beta invariant. So you have actually a whole ton of different expansions for the beta invariant. This is sort of the cryptomorphic thing. You have lots of different ways you can define your anti-matroids, which is why they crop up so frequently in other contexts. People don't realize they're redoing something that's already been done because they've got a different characterization. But you can do a rank. So there's the rank expansion. You can do a free convex set expansion by only summing over the free guys. And you can do a subset expansion by the closure operator. And there are a whole bunch of other expansions of the beta invariant, a Mobius function, Boolean thing. There's a whole bunch of them. Okay. So with anti-matroids, you once again get a deletion contraction, but you subtract the beta invariant for the deletion, and that means you can get negative answers for your beta invariant. So we don't mind negative numbers. We're pretty flexible people, so we're good with this. There's also the same property that if you are a direct sum, your beta invariant is 0, so no reason to worry about it with direct sums. By the way, it makes computations a lot easier. Boop, direct sum, boom, I'm done. Okay, so now I'm going to talk about a few of your favorite things. The hope is. So again, we've got this expansion for free convex sets. Here's the strategy. Given a class of anti-matroids, you interpret what the free convex sets are combinatorially. Then you compute beta somehow. You use your math magic. You interpret the answer combinatorially. Then you remove the beta invariant from your story. You don't tell people that's where you got the theorem from, and you have a new theorem, and it looks lovely and magic. And we'll see an example or so of these lovely theorems that you can get. So let's start with trees, which, as I said earlier, or Gary said, or we both did, trees are anti-matroids. So the ground set is the edges of the tree for this, and a set is convex if it forms a subtree. So the convex sets are just the subtrees. A free convex set is a star because it's not enough to have a tree. You have to be able to remove every edge and still be convex. So there's a nice star. So those are the free convex sets. So the beta, again, is the sum over all the free convex sets. So let's do that for this example. So how many free sets are there of size 1? Remember the edges. So a set of size 1 is just an edge. How many edges are there? Good. There are 9. So what's a free set of size 2? It has to be a star of size 2. That's just a path of length 2. How many of those are there? Have you counted them already while I was going on, giving you time? Go! Very good. There are 11. Just do the little count. Yeah. And, oh, whoops. Okay, how many are there of size 3? Very good. And, yeah, that vertex, and that vertex. So there are 3 of them. So beta is 1 times 9 minus 2 times 11 plus 3 times 3 is -4. -4 what? Well, negative we don't care about. We're flexible. So first of all, for trees, the beta invariant is always going to be negative in this case. And we want to interpret 4 combinatorially. 4 what? So looking at this picture, 4. It's the number of interior edges. So notice that, and that, C, D, E, and F are all interior edges. They're not leaves. And in fact, if T is a tree, then now notice that this is no longer being called the beta invariant because we cleverly removed the beta invariant. You sum over all the stars of the various sizes minus 1 to the size of S times the cardinality of S. That gives you the number of interior edges. And this is now a theorem that doesn't look like it has the beta invariant or anti-matroids anywhere in it. And that sort of, isn't that kind of fun? Okay, so there it is. So you could actually, now that you have a theorem in your hand, you can rewrite it in various ways. The number of leaves, which is the complement of the number of interior edges, you can just do a little jiggle, and you get a second theorem for nearly free. Isn't that excellent? We like new theorems, so there you go. All right, so then notice the comparison with the original Crapo's beta invariant. 0 doesn't count much. So we get, with this new beta invariant, we get sort of an interesting thing. The prototypical anti-matroid, the one that's the one that was on the cover of the book, is finite subsets of the reals. Rn, we're going to look at R2 because it's much easier to draw the pictures in R2. So we're going to take a finite subset of Rn in general. A set is convex if its convex hull intersect the set of your E set is C itself. C is free if it's an empty polygon. Notice if you have this set, A, F, D, E, that's not free convex because if you remove F, the convex hull includes F and it's not there anymore. So we need empty polygons. So this one, is it convex? No, because we're only looking at the outside guys, and there are F inside going, hello, F and E. So it's not convex, it's not free. How about A, C, D, E, F? That is convex. Is it free? No, because again, you can't remove F and have it be convex. So it's convex, but not free. And finally, those guys, A, B, C, E, F, is that convex? Sure. Is it free? Yes. So you notice the free convex that's an empty polygon because now you can remove any edge you like and it stays convex. So yay! So that's what the free convex sets are. So now here's a collection of points. The number of free sets of size 1, those are just the vertices, done. Free sets of size 2, in this case, there are no 3 points on a line. If you had 3 points on a line, that would not be free convex because of that middle point. So numbers of size 3 are triangles, sets of size 4. You have not that guy, so it's not everybody. And the whole thing, the 5, we had our friend over here. That one is convex free, sorry. So here's your beta. It's F1 minus 2F2. Calculate, and you get 2. 2 whats? So the question is 2 whats. We hope that the answer is 2 somethings. So then you do a mazillion examples of calculating. So you take this, and you get beta as 1. You take Orion, which is an excellent constellation. If you're from the southern hemisphere, it looks upside down to you, but we can be flexible. Orion likes to stand on his head half the time. So you get beta equals 3. 2 what, 3 what? So that's the question. And we want to know. So our theorem from a long time ago is if you take a finite subset of R2, then beta of G, which turns out to be positive in this case, is the number of interior points of the configuration. And it doesn't matter if they're on a line, it's just the number of points on the interior. So we conjectured in our proof was disgusting. We conjectured that it was going to bump up for each dimension, alternating in sign. And that conjecture was first proven, thanks Vic, in 2000 using combinatorial topology. Klein gave another proof using valuations on lattices. And then some other people have used elementary geometric arguments in 2004 and 2006. And the motivation, I think, for the last 2 certainly was finding empty hexagons. That was a big problem for a while that has since been solved. So another example of something that people seem to like are chordal graphs. A graph is chordal if it has no chord-free cycles. Okay? vertex is simplicial if its neighbors form a clique. And if G is chordal, what we can do to get an anti-matroid is you successively shell the simplicial vertices off, eventually removing them all. So that vertex is simplicial because its neighbors, it's a clique. This vertex is not because its neighbors aren't a clique. Okay, so now we shell it off, and now suddenly this has become simplicial where it wasn't before. So now you can shell it and shell it and shell it, and okay, there we go, and now we're shelling and whatever. So the anti-matroid structure is on the vertices this time, not on the edges. A set is convex if its complement, if the complement is a simplicial sequence, and C is free if C forms a clique. So those three vertices are a clique, so that's free. Those four sitting in there, that's a clique. So that's what the free convex sets are. So you do the same thing. You sum over the cliques, -1 to the size of clique -1, times the size of the clique, and you get the negative number of cut vertices. So this is a new theorem, and again, notice it doesn't just remove the beta of G, and then you've got a new theorem. And beta of G here is -3, and so you bump up the power there, and that removes your negative sign, and then you're done. You can play the same game with posets. Elements of the poset are our edges. F is feasible if it can be formed by repeatedly removing maximal and minimal elements. That's called the double shelling anti-matroid. You're shelling things off. A free set contains no chains of length greater than or equal to 3. Here you get beta being -1, so we're back to being negative. -1 what? I mean 1 what? So Edelman and Reiner in their paper showed that this is the number of bottlenecks in your posset right there. And again, it's using the beta invariant to give you new theorems. So you can do this for a lot. There are a lot of other anti-matroids. If you take any combinatorial with a reasonable rank function, we can define a beta invariant. Trees using the vertex ground set, not the edges, as Gary was doing. Rooted trees, Gaussian elimination greedoids. Rooted graphs, you can just keep doing this game, and you can get new theorems that are sort of interesting. And that's what we have to say. And we're a little early, so you get to snooze or something. Thanks.